Everett's idea wasn't that we could introduce parallel worlds to solve the measurement problem. That would be a kind of change the physics strategy in a kind of weird one. Everett's insight was if you look carefully enough at the physics we already have, you'll see it's a parallel universe theory all along.
Hello, this is Robinson Earhart here with the introduction to Robinson's podcast number 167. And this episode is with David Wallace, who is Mellon Professor in the Department of History and Philosophy of Science at the University of Pittsburgh. And I was going to mention this later, but an important note on David's bio is that he is a fan of cats and dinosaurs, though he does not own either of them. But I say this because of the cat that is nagging me. And perhaps you can see Mishka the Vishla's snoot at the bottom of the screen, who also requires attention at the moment. But anyway, one of the best things about David, for my purposes and the purposes of the greater philosophical world, is that he is both a physicist and a philosopher. So he obtained PhDs in both subjects from Oxford, and he is best known for his defense of the Everett interpretation of quantum mechanics, which is named after Hugh Everett. And it's also known as the many worlds interpretation because it entails that we live in a multiverse. Though this multiverse is very different from the Marvel multiverse, which everyone will be familiar with, because in this multiverse, there are many things that are different, but one is that the universe is constantly splitting. And what's most surprising about this to me is that it's the most basic, bare bones reading of the quantum mechanical formalism. And anyway, David and I get into all of this and the history of the interpretation, as well as how it relates to other questions like the broader question of realism in the philosophy of science. So to what extent should we be committed to the unobservable objects, or in this case, bizarre implications of our best scientific theories? We get into some of the strong points of the Everett interpretation and some weak points, such as, potential weak points, such as how we're supposed to explain probability in the multiverse when every single possible outcome of an observation obtains in some branch. So David's book on the subject is called The Emergent Multiverse. There's a link to it in the description. And I have to mention that reviews, likes, subscribes, comments, follows are all very much appreciated. There are some relatively new t-shirts, one featuring Pins the Podcat on robinsonsfashionempire.com that you may or may not be interested in. So now, without any further ado, I hope that you enjoy this conversation as much as I enjoyed having it with David. You started out in pure physics at Oxford, but then after obtaining your doctorate, you worked toward another one in philosophy and have since then worked in philosophy departments, though of course your research is mainly in the philosophy and foundations of physics. And I was wondering what it was about the different approaches to physics, one in a physics department and the other in philosophy, and the questions they're both interested in, that made the latter world seem like the right one for you.
So the answer in some ways is quite boringly institutional. The PhD I did in physics was one where my supervisor gave me a possibly unwisely large amount of latitude to do whatever I wanted. I ended up hanging out a lot with the philosophy of physics people in Oxford, and a lot of the questions I was thinking about were very conceptual, foundational questions, the kind of thing that doesn't lend itself to experiment or direct calculations. Those are the kind of things I was interested in, but it became increasingly clear by the end of my physics PhD that if I wanted to carry on pursuing those lines of research, I was going to find it very hard to make a career of it inside the structure of physics the way physics departments are structured in Britain and in America, which tends to, for good reasons and bad, tends to emphasize the concrete and the calculational. So I thought either I'm going to change the direction of the research I'm doing, which I wasn't very minded to do, or I'm going to explore whether I could do broadly the same research, but with the right kind of credentialing to be employed in a philosophy department. So I don't want to sound too cynical about that. I learned an enormous amount of useful things in sort of formal graduate study in philosophy, and certainly that opened up research trajectories I wouldn't have followed otherwise. But to a significant extent, it was more a matter that the questions I was already interested in were just not set up to be the kind of thing that would be good for pursuing a physics career on, whereas it was something that was well set up to pursue a philosophy of physics career.
Well, this points to a couple of deeper questions, but the first one is, do you have any insight into this rather strange bifurcation in the sociology of physics, that these foundational questions, which really seem vital even to an outsider for understanding the world, why they've been relegated to philosophy departments? It seems somewhat analogous to the situation in math, where logic is as often as not done in philosophy. But in addition to that, seemingly mathematically substantive questions about the nature of infinity or the objectivity of various results, they're also exclusively philosophical provender.
I feel I should sort of fight against the claim that these things are relegated to philosophy departments. Have a more peaceful coexistence than that. But putting that aside, yeah, it's pretty interesting. So to some extent, I think this is sort of Thomas Kuhn themes in philosophy of science. I think that when a science, and in this context I count math as a science, has developed a certain methodological maturity whereby there are certain methods and approaches that are highly successful at making concrete progress, then the infrastructure of the subject becomes rather less built around alternative methodologies. So something like the structure of mathematical proof would be an example in mathematics, to go to your example there. Why don't mathematicians spend time deeply thinking about the nature of infinity rather than just proving more theorems? Well, the tools of mathematics are extremely well suited to deepening our mathematical understanding through the proving of theorems and the stating of conjectures and the exploring of generalities. And they're not very well suited to sort of deep thought about the nature of infinity, except insofar as you can turn that into some concrete, mathematically phrased question. And I think something somewhat similar is going on in physics. Physics paradigmatically is experimental, and so the gold standard in physics tends to be where you can do some contribution that's testable. A lot of theoretical physics doesn't make that doesn't sort of get over that hurdle in itself, but it contributes to the ability to calculate something concrete that plugs into that kind of quantitative improvement in our understanding. And the sort of the methods and the culture of physics come to validate that. And as in a half-hearted defense of how it does that, it has to be said that it's partly, I think, about whether the discipline has the internal tools to distinguish good work from bad. So a dirty little secret of foundational work in physics is that a lot of it is just really not very good. And often I think it's hard to distinguish a bad foundations of physics paper from somebody who just didn't really understand their grad level statistical mechanics course or something and is acting out their confusions in their work. Most of that doesn't get published, but there's a lot of it out there. And so you can understand why that kind of foundational work, which doesn't lead to proofs or theorems or calculated quantities, let alone experimental results, is the kind of thing that physics is a bit institutionally suspicious of. But I think mostly it's those kind of institutional structure issues. And another part of that, again, is that physics is in the sort of paradigm of the sciences where the money tends to come from research and the research follows the grant, and the grant is awarded according to the sort of themes of work that's been done. So there's not so much space to do things between the cracks of established research programs. What you find actually is that good foundational work done by physicists is by and large done by physicists who are already tenured and who've already established themselves and their credentials and their job security, I suppose, through more conventional physics routes, and that then gives them a bit more freedom to explore and contribute in different ways. Those are my thoughts, anyway.
That makes total sense to me. I mean, so many disciplines, physics, biology, and so on, began as part of philosophy, or at least continuous with philosophy. But as the methodologies became more developed and the questions tractable, they then branched out.
Yeah, I mean, people often say, why doesn't philosophy make progress? And I think the main method by which philosophy makes progress is the aspects of intellectual study that we used to call philosophy made so much progress we stopped calling them philosophy. I mean, it used to be a philosophical question what the nature of matter was, or how we should understand motion, and those are now those are philosophical problems that we've done so well at answering that we've now put them in a different discipline and call them a different thing.
Mm-hmm. Yeah, totally. And then the other direction in which your first response pointed me is, what was it though just about these more conceptual questions that experiment couldn't really settle that interested you more than, say, building telescopes or observing or just working at a blackboard predicting what might happen at CERN?
Yeah, I mean, I would have been at the blackboard anyway. I'm far too butterfingered to actually build anything. It's a good question, and I mean, in a sense, you're asking about my psychology, and I'm not sure I entirely know the answer. I think there's a perfectly plausible way things could have fallen slightly differently where I would have done exactly that. I can tell you why I'm extremely interested in the questions I'm interested in, but I'm also extremely interested in a lot of the things that more mainstream theoretical physicists do. And it's just, there are only so many hours in the day and so many lives you get to lead. So, I'm not sure there's anything very deep about the fact that I'm doing this kind of work rather than string theory or theoretical astrophysics.
Well, then maybe we should move on to some of the substantive questions that you have been working on. And much of your work has centered around the many worlds, or Everett theory of quantum mechanics. And I will defer to your judgment here, because I think that there are at least 3 things that we ought to touch on before we get to many worlds. And maybe there's more, maybe there's less. But the first thing is, one, just who Hugh Everett was. And then the other 2 crucial parts of the story are the measurement problem, and then the tension between realism and instrumentalism as they relate to quantum mechanics. So I'll leave it to you. Where do you think we ought to start getting many worlds on the table?
Goodness. Well, I mean, maybe it makes sense to start by talking about the measurement problem. And it's, as you say, it links into those kind of realist instrumentalist themes. So here's my kind of quick summary of the measurement problem. Quantum mechanics is our best theory of the very small, but big things are made of small things. So really, quantum theory is our best theory of basically the whole of physics. It's amazingly successful, but we have serious trouble understanding the theory as a description of reality. As a sort of tool to calculate things, it works really well. But when we try to understand the theory, and often we need to understand it even to apply it, let alone to explain it or internalize it, it seems to be saying things that make no sense. So in particular, quantum mechanics seems to say that whenever something can have one property or another property, it can somehow have both of them at the same time. It's a thing that the technical term is superposition, but you can think about it as somehow having both properties at once. So if a particle can be here or there, it can somehow be here and there at the same time. If it can be moving this way or that away, it can be moving both directions at the same time. And while you could just say, okay, fine, that's subatomic particles, we aren't evolved to understand subatomic particles, maybe that's just a weird thing subatomic particles can do that we can't do. But the theory also seems to say that if you measure a particle that's doing 2 things at the same time, then that kind of weird superposition, 2 things at oneness, sort of magnifies upwards to the macroscopic scale. So if the particle's here and there at the same time and you measure it, then your measurement device says it's here and it's there at the same time. If you unethically connect the measurement device up so that if the particle is here, your cat gets killed, and if it's there, it doesn't, then if the particle's here and there at the same time, your cat is alive and dead at the same time. That doesn't seem to make sense. Even insofar as it makes sense, it doesn't seem to conform to our observations. You can kind of fix that in a very ad hoc way by saying, As soon as you get to the macroscopic level, as soon as you start talking about not atoms and molecules, but measurement devices and humans and cats, suddenly we don't understand quantum mechanics as saying two things are happening at the same time. We understand it as saying one of them is happening or the other one is happening, and we don't know which one it is. There's a sort of transition in how you understand the theory that's supposed to happen when you go from the small to the big. But that's very unprincipled. No one's got a good story as to how that is, or how it can be that the theory sort of suddenly stops working and works in a different kind of way. Because if you take really literally that idea that suddenly it stops being the two things are happening at the same time, what you're saying is that the equations of quantum mechanics suddenly have to fail at some scale, and then there's some random process that kicks the system into one way of being or another way of being. No one's ever found empirical evidence of that process, and it's very hard to build into our equations. But it's difficult to see how we can understand the theory without having something of that kind going on. That's the measurement problem. It's the problem that we don't seem to be able to make sense of our theories, and insofar as we can make sense of them, then we can only do it in very unprincipled ad hoc ways.
So just to reiterate, make sure that we're totally on the same page. So quantum mechanics is a very powerful predictive tool. I mean, quantum field theory has been verified up to 14 decimal points, I think, something to that effect. But there are these strange features of quantum mechanics that make it difficult to wrap one's mind around. So non-locality, the wave-particle duality, entanglement, all of these things. And to the extent that we can make sense, to echo your last sentence, of these strange features, it seems to have to be done in, to use your word again, a very ad hoc way.
Yeah, I think that's about right, yes. And those terms about entanglement and non-locality and the wave-particle duality you bring up, at the level of this discussion, those are all sort of different aspects of the fact that the theory seems to force us to understand particles as doing multiple things at the same time, and not simply doing one thing or another.
Right, which very much it does not reflect our macroscopic picture of the world.
Right, yeah, you have a cat, I think. I'm guessing you've never seen it alive and dead at the same time.
No, I haven't. There have been some scary moments where in the middle of the night I can't tell what's going on, but yeah, I've never caught her in the act of being alive and dead at the same time. So, okay, how do responses to the measurement problem align with maybe this landscape of instrumentalism on the one hand, pure instrumentalism on the one hand, and realism on the other hand? There are some finer grained distinctions. I talked to of course, there are plenty of finer grained distinctions. I talked to Lee Smolin on Sunday, and he threw magical realism in there as well. I don't know if you've heard this, but
I mean, here's how I'd think about it. Let's not think about the contrasts between realism and specifically instrumentalism. Let's just think of it as the contrast between realism and just the denial of realism. So realism, what I have in mind here, is something like our science is in the business of giving us a third-party description of the world. It says what's actively, objectively going on in the world. It doesn't say what's going on as perceived by a certain person. It doesn't say what's going on from the perspective of a certain person. It doesn't say what someone should expect to see or hear. It just says what's going on. End of story. So Newtonian physics is the paradigm case of this, if you like. Newtonian physics doesn't directly say this is what you should expect to experience. It says this is what's happening. And then there's a secondary epistemic question about what you should expect to experience, which is an important question to answer if you want to test the theory. But the theory itself is totally understandable, makes total sense, without the presence of the observing perspective. Indeed, you could understand the theory if there were no humans in it at all. And most of science is like that. I mean, our theories of genetics talk about the DNA molecule as just an objectively present thing with objectively present properties. It's not DNA for you or DNA for me. It's just DNA. So one class of solutions to the measurement problem drops that realist assumption in one way or another. So you might just want to be in a sort of out-and-out instrumentalist and try to say our theories are simply devices to make predictions, and that's the end of the story. You might want to say, a little more subtly, that our theories are intrinsically first-personal. There's a role for the observer that can't be separated out, that sort of Newtonian third-party concept of science just isn't adequate to the quantum universe. There's a bunch of different ways you might try to change philosophy so that the sort of flat-footed contradictions in the measurement problem go away. And alternately, if you want to leave philosophy largely unchanged, the natural thing people tend to think about is changing the physics. They want to say, okay, if the equations of quantum mechanics predict that cats are alive and dead at the same time, so much the worse for the equations of quantum mechanics. Okay, yes, 14 significant figure predictions, blah, 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 but nonetheless, doesn't matter how good the predictions are, it made the prediction there's a cat that's alive and dead at the same time. There isn't a cat that's alive and dead at the same time. The theory needs changing. So that kind of changed the philosophy and changed the physics route. That's how I tend to dichotomize. God, that's being very jargon, so sorry. That's how I tend to think about the choices in sorting out the measurement problem. Except that I'd say the Everett interpretation, the many worlds theory, is what you get if you decide, well, I'm not very happy changing the physics or the philosophy.
Do you think it is at all a fair, although reductive gloss to put on realism, to say that if one is a realist about the theory, then one takes a somewhat Quinean attitude toward it and feels committed to the sorts of objects and processes that, well, the objects it quantifies it over, or the processes it describes?
Interesting. I mean, yes and no. I mean, I think it's sympathetic to the very general sweep of Quine's perspective. In other words, the realist says, here's my theory. This is what my theory is saying. I have no better guide to the world than what my theory says. I have no better guide to epistemology than the scientific method. So if this is what my theory is, then that's what I'm committed to. Whether you want to follow Quine further into the kind of our goal should be sort of regimenting our theories in a first-order logical framework and then committing to the quantificational claims they make, I'd say that's a substantive assumption about what our theories would be telling us that Quine's making. I actually think Quine's probably wrong for reasons that are a bit at right angles to the many worlds theory and to do with the way we use mathematics to represent. And I think that kind of what are we committed to quantifying over presupposes certain things about the way scientific theories are stated that Quine is just wrong about. But I think the broad Quinean spirit is absolutely very sympathetic to that sort of realist position.
Just to
by the way, sorry, just pausing a second since you can edit this. I was answering that one at a relatively high level because you moved into the philosophy point, but I wasn't sure quite at what level you wanted an answer to that.
Totally fine. No need to think it all. I try not to think these things over too intensely. Just wondering if what you have in mind is anywhere in the ballpark of you just don't want to be. You don't think that using math in physics, for instance, commits us to the existence of mathematical objects. They're just sort of a descriptive tool.
So I think something slightly different from that. I think this is a slightly different topic, but it's interesting in its own right. I think that the way physicists use math to model the world, while it can be cast into a kind of object property relation language, normally can't be uniquely so cast. And trying to do that tends to lead us to try to draw distinctions that physics doesn't really care about. So, for instance, physics talks a lot about fields, and what's a field? Well, you might want to say, look, a field, when I say there's a field permeating space, you could say, well, I mean, there's a sort of physical entity, an extended thing, and the parts of that entity sit in parts of space. Or you might mean, well, field is a sort of façon de parler for saying that all the entities in the world are the points of space, and the points of space have field properties. So in the one case, your ontology includes both the points of space and the parts of the field, and your ideology includes a whole bunch of occupation relations. On the second version, you've got a much sparser ontology, just the points of space, and a different ideology that just consists of field strengths. According to the sort of classic Quinean way of playing the ontology game, those are sharply different positions, and metaphysicians argue about which is right. Physicists don't give a damn between those positions. They're mathematically equivalent. The math that you'd use to model the one and the other are the same or intertranslatable by translation schemes that physicists don't regard as content changing. So in my view, if you want to say how do we read content of physics, you're led to something a bit more structuralist, a bit closer to the sort of structural realist ideas that have been in vogue in the last 20 years or so, and a little less Quinian.
Okay, thank you very much for entertaining my quite tangential questions to the topic at hand. But okay, so we've got the measurement problem and realism and instrumentalism on the table. So I have the sense that Hugh Everett is somewhat of a character, and he didn't really have a classical physics career or career as a physicist. So just who was he before we get into his deep insight?
Sure. I mean, I should be honest that I'm not the kind of philosopher who's done a very deep study of the historical figures, so my grasp of Everett's kind of surface, but I can give you the highlights. So Everett was a grad student of John Wheeler. Wheeler is a very eminent post-war physicist, worked on the Manhattan Project, moved into general relativity, was kind of an eminence grise of American physics for a very long time. Everett was his grad student, I think in Princeton around the mid to late 50s. And he was interested, among other things, in this measurement problem we're talking about. And to translate really anachronistically the way I described the measurement problem a minute ago, what Everett asked was, is it really the case that we know that we don't see cats alive and dead at the same time? And that's a set of ideas that led him to thinking about what was actually going on physically in the process of measurement. How do you model measurement inside quantum mechanics? And I'm sure we'll come back to what that involved, but just to close the brackets on his own story, he had a pretty rough ride with a set of ideas from Wheeler. Wheeler wanted him to go and talk to Niels Bohr in Copenhagen, who's one of the founding fathers of quantum mechanics. Wheeler wanted Everett to make sure that Bohr was okay with his ideas. Bohr was not okay with his ideas. Wheeler put a lot of pressure on Everett to really censor an awful lot of the material that went into Everett's published dissertation and the paper that came out of it. I mean, if you think academia has a conformity problem now, you ain't seen nothing yet. Have a look at physics in America in the 1950s. So it's certainly true that Everett's ideas got very heavily, suppressed is too strong, but a lot of the pieces of them were suppressed, and what was publicly communicated was much smaller than Everett's original set of ideas. And in fact, we only really got clarity on what Everett himself wanted, nearly 50 years later, when a lot of his papers became available. Everett then left physics, and the obvious way you tell this narrative is that Everett was driven out of physics by the fact his ideas were not taken seriously enough. I'm not at all convinced that was actually true. I mean, what Everett went off and did was work in, I think, the Rand Corporation, some of the kind of military-industrial complex that was growing up in the Cold War. They wanted scientists. They wanted people with Everett's technical skills. They paid pretty well. Everett was interested in that stuff as well. I mean, he had a bunch of different things that interested him. I think the story as to why he actually decided to leave academic physics and go and work for Rand is kind of complicated and multifaceted. But anyway, he then basically spent about 30 years in that work. He was, it would be unkind, but not completely unfair to say that his research was largely focused on how to maximize casualties from nuclear attacks. Maximize, you understand, how we can best deploy our own nuclear weapons to maximize the other side's casualties. He was very involved in that kind of thing. My sense of exactly what he was doing there is kind of vague. Frankly, I assume a lot of it's still classified. He certainly had a very colourful and difficult personal life, the details of which, frankly, are messy enough that I don't know them well enough that I don't want to accidentally overstate or pass on rumours. There are plenty of sources for this kind of thing, but certainly he had significant substance problems. He died quite early. He had major health issues, and he died sometime in the 80s, I think.
Well, this censorship you mentioned, I noticed already in the book, at the beginning of your book, the Emergent Multiverse, which I'll name it, of course, in the introduction, but it's the Emergent Multiverse, quantum theory according to the Everett interpretation. The epigraph is a little bit that was cut from his thesis at the urging of Wheeler. And while you were talking, I pulled it up, and maybe, we don't have to talk about it right now, but maybe I'll just read it just so people can get a sense of how he wrote, because he was a nice writer. So, okay, what he wrote was, we have then a theory which is objectively causal and continuous, while at the same time subjectively probabilistic and discontinuous. It can lay claim to a certain completeness, since it applies to all systems of whatever size and is still capable of explaining the appearance of the macroscopic world. The price, however, is the abandonment of the concept of the uniqueness of the observer, with its somewhat disconcerting philosophical implications. And those three, just as three sentences, it's quite powerful. There's a lot there. But also I have the sense that his thesis was quite short, quite to the point, and then he just basically left physics.
I think that's right. There's almost a sort of mic drop aspect about it.
Yeah, exactly. But, okay, cool. Well, this leads us to what you bracketed this, what his major insight that led to this new quantum theory, the many worlds or Everett interpretation or theory. Actually, since we've been jumping around a bit, I should also ask how you feel. You write about this a little bit in the Emergent Multiverse, but how you feel about the term interpretation or theory, because as Tim Modlin has stressed to me, they are different theories. Like Bohmian pilot wave theory is a different theory from many worlds. In the many worlds theory, I almost said interpretation. They are not merely different interpretations. So this, I think, leads to a lot of confusion in the lay population.
Yeah. So it's a little subtle, and I half agree with Tim. So what I'd say is we've got a theory, or at least the formalism that's the core of a theory, in what I'd call unitary quantum mechanics. And that's the physical theory that physicists are in practice using to calculate. And that's the kind of thing you learn as a student, is the kind of thing you work with if you're a professional physicist doing calculations in quantum mechanics. The kind of default interpretation of that theory is the kind of ad hoc mess I was talking about earlier. Now, you can then distinguish between what I'd call pure interpretations, which leave the mathematical formalism of the theory alone and tell you how to make sense of it, versus new theories. To go back to my framework earlier, if I have a change the philosophy way of solving the measurement problem, I'm probably leaving the formalism of quantum mechanics alone and just trying to make sense of it. If I have to change the physics approach to quantum mechanics, I'm going to be genuinely using a different theory with different equations and different calculational content. So in that sense, I certainly agree with Tim that, with Maudlin, that the de Broglie theory is a different theory from the many worlds theory. I'm less keen on saying that the many worlds theory is a different theory than, orthodox textbook quantum mechanics, rather than a different interpretation of the same underlying mathematical structure. Now, Tim, among other things, individuates theories significantly more finely than I've just done. And Tim would also want to say that we can't make sense of the framework, which is exactly what forces us to change it. But then those are substantive philosophical points on which people can differ. But I think there is an important distinction between those approaches to quantum mechanics that effectively require us to do new physics, to change the theory, at least the way physicists individuate theories, and those approaches that don't require us to do that. And I tend to use the word interpretation to cover the latter ones. That's why I tend to talk about the many worlds interpretation, the Everett interpretation, more than the many worlds theory. And I should say a lot of the reason why I'm attracted to that kind of way of doing things is that I think changing our physics is kind of hard. And the de Broglie theory is a very nice toy model to explain a few very simple quantum things, but we're many, many decades behind the current stage of empirical success of physics.
Mm-hmm. Yeah, that's my quite limited understanding as well. So thank you for, again, entertaining a tangential question. But let's go back to Everett and his thesis and this new insight?
Okay. So here's the thing. The way I set the problem up earlier, I was saying, well, look, changing the physics is difficult, changing the philosophy is difficult, but it looks like we have to do one or the other because the theory by itself, taken realistically, says cats are alive and dead at the same time. And when we look at cats, they're clearly not alive and dead at the same time. Well, Everett effectively asked, he didn't use the cat as the example. I don't think Schrodinger's cat was a famous example for a while longer, but he effectively asked, well, what would it actually look like if you saw a cat that's alive and dead at the same time? And I think intuitively it would kind of look like a fuzzy cat, like you're seeing double, or you'd have way too much to drink or something. But intuition isn't a great way to work out what would happen in a scientific experiment. If you ask the theory what happened if I look at a cat that's alive and dead at the same time, well, the theory says if I look at a cat that's alive, then I will have to go into some physical state that records my observing the cat as alive. I have some neurological state in which seeing the cat as alive is encoded in my memory and cognitive processing. And there's a different state I'll go into if I see a dead cat, where my neurological state is different, my neurons are fired differently, maybe what I've written down on my lab notebook is different, if you want to be less psychologized about it. So in that case, given the mathematics of the theory, at a slightly technical level, given it's a linear theory, then if the cat's alive and dead at the same time, and I look at it, then I go into a seeing the cat alive and a seeing the cat dead state at the same time. I don't go into some third state that you could call seeing a weird cat. I mean, again, there's a perfectly plausible neurological state I could go into where somehow I'm seeing a fuzzy superimposition of two cats. But quantum mechanics doesn't predict I go into that state. It predicts that I, at the same time, go into the seeing a live cat state and the seeing the dead cat state. And it's all correlated. So that me and the cat, at the same time, go into the cat's alive, I see cat alive state, and the cat's dead, I see cat dead state. And if I tell you about it, then you and me and the cat are now in a cat alive, David sees cat alive, David tells you the cat's alive, plus cat's dead, David sees cat dead, David tells you the cat's dead state. And if you then announce the result on the podcast, then all your audience go into, at the same time, hearing that the cat's alive and hearing the cat's dead. And again, all of this is correlated. So the whole of the planet, pretty quickly, is at the same time doing two separate things. It's doing a as if the cat was alive thing, and it's doing a if the cat's dead, as if the cat was dead thing. And both those processes by themselves are ordinary and mundane and just describable in classical everyday terms. And they don't interfere with each other. In quantum mechanics for microscopic systems, the whole reason we have to say things are doing two things at the same time is they have a weird thing called interference, which is kind of like the particle being there affects the particle being here and vice versa. But for well understood dynamics reasons, that interference goes away when things are big enough. So really, the live cat goings on and the dead cat goings on are completely independent of each other. And what does it mean to say, well, physical reality is instantiating two completely different processes, a live cat process and a dead cat process? Well, it means there are two chunks of physical reality. There's a live cat chunk of physical reality and a dead cat chunk of physical reality. And so in slightly picturesque world terms, there are two worlds. And the experiment caused the world to split. Initially it caused the cat to split, then it caused me to split, then it caused you to split. And really the processes that are causing the splitting aren't us talking, they're going out much faster than that. And so the idea is that the theory, it's not that Everett's idea wasn't that we could introduce parallel worlds to solve the measurement problem. That would be a kind of change the physics strategy in a kind of weird one. Everett's insight was if you look carefully enough at the physics we already have, you'll see it's a parallel universe theory all along. It's helpful to think that these aren't universes in some kind of fundamental sense. So, David Lewis, the philosopher, talks about possible worlds as sort of concrete, actual different worlds out there. But those are exact, they're fundamental, they're in the deepest structure of reality. These aren't worlds in that sense. They're worlds in the same way that planets are worlds. So Earth and Mars are worlds. Why? Because Earth and Mars don't interact with each other very much. Well, stuff on the surface of the Earth and stuff on the surface of Mars basically leave each other alone until someone sends a space probe. Mars is a robust, self-contained system, so is Earth. But there's no exact blocking of interaction in Earth and Mars. There's no exact moment where you leave the atmosphere of Mars and go into interplanetary space and reach Earth. You certainly won't find Earth and Mars in our fundamental physics. They're emergent ontology, emergent stuff. And the claim in the many worlds theory and the Everett interpretation is if you look carefully at the mathematics of quantum mechanics, you'll find that that kind of multiple worlds is just built into the way the theory in fact evolves. So the idea is that you haven't changed the physics, and in some sense you haven't changed the philosophy either, because this is still a third-personal realist account of what's going on. You've just got whatever it calls this disconcerting implications. You've got lots and lots and lots of other versions of me out there in physical reality.
So, again, just to recapitulate, to make sure that I'm on the same page, where we began with, the measurement problem arises quite basically from things doing multiple things at one time, which diverges from our classical picture of the world. And the way that Everett explains this, his insight, is that each of these different things happening at the microscopic level corresponds to a different world, but it's not an ad hoc addition. It's what follows from the physics of the theory.
So that's nearly right. It's often what you'll see in popularizations of it. From a philosophy point of view, it's not quite right, because what's justifying this language of worlds is that I've got sort of separate autonomous chunks of reality doing their own thing and not interfering with each other. That means that the world language can't be extrapolated all the way into the microscopic. So if I've really just got an electron that's here and there at the same time, I don't really have any good grounds, other than maybe metaphor, to say, well, that means there are two worlds, an electron here world and an electron there world, because the electron here and the electron there they're not separate strands of reality. They're interfering with each other in the jargon of quantum mechanics. They're not decohering in that jargon. The point at which we're allowed to really talk about worlds is the point at which we really have sort of separate autonomous strands of physical reality. And that normally happens when things get large enough that these quantum interference effects become unobservable, because they're kind of just sort of dispersed over zillions of other particles. This is why my book is called the Emergent Multiverse. Quantum mechanics isn't a fundamental multiverse. Again, not like Lewis's picture. If you look at a sufficiently fine grain, you don't see the multiverse at all. You just see quantum mechanics.
And this is getting ahead of myself, but this divergence that comes when you get to a larger scale, this relates to decoherence theory.
That's right, yeah.
Okay, great. Well, before we move on, though, just to be quite explicit again about Everett's insight, you said that, or you wrote rather, that there are two components to the interpretation. There's a contingent physical postulate, and then there is an a priori claim. Could we just lay those two out on the table?
So the contingent thing is the physics we have. It's the dynamics of our world is in fact a dynamics whereby at the fundamental level things simultaneously coexist with many properties, and at the emergent level the world separates into kind of largely non-interacting layers, each of which looks autonomously like ordinary definite goings on. That didn't need to be true. That's a contingent fact about the way our world is structured. There's then an a priori claim about the way we understand the relation between higher level and lower level ontology and the way in which we understand physical theories at all. And that claim would be that if I've got a claim about the world being structured in a certain way, that's all the work I need to do to justify the fact that the world is that certain way at a higher level. So all I need to do to justify my language of worlds here is to say that the mathematics of the theory is simultaneously instantiating multiple world-like goings on. There are philosophers and metaphysicians who want to say, no, you have a stronger obligation than that. You have to say, for instance, that all of our understanding of the world must supervene on some distribution of fundamental things in space and time, and that the world can only be such a distribution. You might have a view that somehow it's a priori necessary, that the perspective of the observer is playing a key role, which is not in the structure. There are lots of different routes by which one might diverge in one's philosophy of scientific interpretation. But that, in a certain sense, is not the kind of thing that could be different given different empirical possibilities.
Some of the problems that much better educated philosophers and physicists than I have with the many worlds theory that we'll get to later, largely psychological, are what preclude my fully buying into the theory. But one of the most powerful points in Everett's favor, from my perspective, is just how it really follows to a T quantum theory.
Exactly. Yes.
Yeah.
Yes, we have, I think, very good reasons for being scientific realists and thinking that our scientific theories are in the business of giving us objective third-party descriptions of the world. I mean, there are quite good a priori reasons you might think that, but also just if you look at science generally, that's what's in the business of doing. I mean, in the wake of quantum theory in the 1930s, people like Niels Bohr speculated that the whole of science would be rewritten to accept this sort of new perspective on things, but it hasn't been, in fact. The kind of third party, humans are just more physics, humans just do physicsy stuff, the world gets on with things. That picture of science is just reigns effectively. So the case for scientific realism is awfully strong. And the case for the formalism of quantum mechanics is awfully strong. It's by a huge chalk the most predictively successful theory in human history. It's descriptive all the way up to why the galaxies across the night sky have the structure they have, all the way down to the Higgs boson. It underlies everything that we're doing, really, from computers, nuclear weapons, for better or worse, everything we know about the nature of matter. It's just an extraordinarily successful scientific theory, and trying to change that theory to resolve a philosophical problem is a very high-stakes move. It's kind of telling that the people who want to change philosophy and move away from scientific realism are usually physicists, and the people who want to change physics and alter the equations are usually philosophers. And there are exceptions in both schools, but by and large, you worry that sometimes people don't realize just how large a task it is either to rethink the whole way we think about scientific theories or to redo the mathematical core of quantum mechanics. And so the huge attraction of Everett to me, and this is a bizarre thing to say about a theory that posits parallel universes, is how extremely conservative it is, both as physics and as philosophy.
Mm-hmm. I think it's also an important point in favor of quantum mechanics that you didn't mention, that the two leading theories of quantum gravity, so string theory and loop quantum gravity, are both fundamentally quantum mechanical.
Yes, no, that's right. The only thing I'd say back to that is, if I wanted to make the case for, say, Bohmian hidden variable theories or dynamical collapse theories, I'd say, well, the reason our fundamental theories of quantum gravity are unitary quantum theories isn't that we've got a ton of evidence that's true. It's that the people developing them don't take the measurement problem seriously, and so they've tried to extrapolate unmodified quantum mechanics into the realm of quantum gravity rather than trying to solve the measurement problem and then try to do quantum gravity with the modified theory. I'm not hugely moved by that argument, but it's not a foolish argument. There's some case to be made there. I mean, there's a variant of your point which I think has more power, which is to say, you might imagine as of 1930, when mostly we just had the non-relativistic starting point of quantum mechanics, then you might think that we didn't know how widely quantum mechanics was going to be applied. And then we had 50 amazingly successful years applying quantum mechanics all over the place, and all the time and all the place, the thing we were applying was the unmodified quantum mechanics, and attempts to explain anything novel by using modifications or supplementations of quantum mechanics got us precisely nowhere.
Well, before we get back to Everett or to some of the specific issues that came up, like decoherence theory, I feel like one other character that is worth bringing up is Bryce DeWitt, who I take made the explicit connection between Everett's theory and the implication of many worlds, perhaps because this sort of thing was suppressed by Wheeler.
Yes, the history of this is kind of interesting. I mean, Everett's 1957 paper, which was the only thing he published on this at the time, doesn't say anything about many worlds. It's quite a coy paper, and it's so coy it was genuinely controversial for a long time whether Everett had a many worlds reading in mind at all. DeWitt wrote a very influential piece in Physics Today in early 70s, I want to say, that was extremely explicit about the many worlds reading. And DeWitt and I think one of DeWitt's students, DeWitt and Graham published an anthology of work on Everett, which was explicitly called The Many Worlds Theory of Quantum Mechanics, and which also published Everett's longer thesis for the first time. And so it's absolutely right that the language of many worlds enters these discussions explicitly through DeWitt. That said, it's completely clear from Everett's later unpublished writings, once we have them, that Everett was thinking in many worlds terms. I mean, that quote you read earlier from the introduction to my book is just as clear as day, that Everett's thinking there were going to be multiple observers in this story. And Everett was in correspondence and conversation with DeWitt. So I think, while I'm not a historian of these ideas, I think it's probably the case that DeWitt got the many worlds idea from Everett, rather than it being something genuinely new that he added to the story. But it's certainly something genuinely new that he publicized through it. And of course, it's probably right to say that DeWitt had latitude to do that Everett didn't. This kind of goes back a little bit to what we were saying about foundational work in physics earlier. Everett, the grad student, was not in a position to publish and defend the full radical aspects of his ideas. DeWitt, the enormously eminent quantum field theorist at the peak of his career, could perfectly well get away with doing it.
Well, I guess one last thing then, I'll probably keep appending last things that I think would be really helpful to put some more meat on the bone, so to speak, for our listeners, would be running through maybe one of the classical experiments of quantum mechanics and how the many worlds theory would explain them. I think the double slit experiment is a good place to start, just because that's an easy way to contrast it with, so like Bohmian mechanics, where the wave is guiding the particle. It would be nice to, sum over histories. The experiment is a good way to explain all of them.
Yeah, okay, good. So here's the sort of classic way you do a quantum experiment of this kind. You prepare the system in a two states at once kind of a state, and then you evolve things so that the two possibilities interfere with each other. So let's suppose it's a bit conceptually simpler to do a sort of discrete possible place of the system could be that the two-slit experiment can be quite fiddly in its details. So imagine I've got a particle, and I can split the particle so it either goes left or right. And then I can bring I've got a left-hand particle beam and a right-hand particle beam. And then I bring the left-hand and right-hand beams back so they cross over each other. And I set things up so if a particle was originally in the left beam, then it'll evolve into being in the left beam and being in the right beam at the same time. And if I've got a particle in the right beam, likewise it evolves into being in the left beam and the right beam at the same time. And it's tempting to say, well, that language of being in both beams at the same time must just be picturesque. What you really mean is it's in one beam or the other, but we don't know which one. The problem with that is that we know that if the particle's definitely in the left beam, it could be seen continuing to the left, or it could be seen going right. And we know that if the particle's in the right beam, it could be seen going left, or it could be seen going right. So if it's just that we don't know which beam it's in, our prediction is that we might see it on the left, we might see it on the right, and if we send a whole bunch of particles through the system one at a time, we're going to find a bunch of them end up on the left and a bunch of them end up on the right. That's what you predict if these quantum superpositions are just fancy ways of saying one or other thing is happening, we don't know which. If you set this experiment up right, and it's a delicate game to get it exactly right, but you can organize it so effectively the left-hand beam can cancel out the right-hand beam, and it can do it even if I only send one particle in through at a time. And so you can arrange things so that if the particle can go either left or right, then at the end of the experiment it definitely goes right. Or you could set it up so it definitely goes left. And that's just inexplicable if we just don't know whether the particle went left or it went right. It's only explicable if we want to say that somehow something went left and something went right. So that's the sort of microscopic story about what's going on. And in a certain sense, that's common to pretty much any attempt to solve the measurement problem that's realist. So Bohm's theory, for instance, effectively says something goes left and something goes right. The something, if you like, is an excitation of the quantum wave function or something. In the de Broglie-Bohm theory, there's, as well as the somethings that go left and somethings that go right, there's a something else that, say, only goes left. But it's still crucial that the something is exploring both possibilities. Some physical thing is exploring both possibilities. Then the problem for any account of that kind is to say, well, how do you reconcile that with the fact that we only ever observe one possibility? And so, roughly speaking, dynamical collapse theories change the equations of quantum mechanics so that even though at the microscopic level the system is doing both left and right, when we measure it, somehow the system makes a spontaneous stochastic jump so that only the measuring left occurs and the measuring right is wiped away, or vice versa. And hidden variable theories like Bohm's say, as well as the quantum thing that goes left and right, there's a particle that either goes left or it goes right. And the particles are what the stuff we see in here and are made out of. And the quantum thing that goes left and right at the same time is a weird kind of ghostly thing that is physically important, perhaps, but which is not the kind of thing chairs and tables and cats and dogs are made out of. And Manuel's theory says, yeah, it's really true at the macroscopic level that what you measured something on the left and something on the right at the same time. It's just that when you think that through, you'll realize that that corresponds to two separate versions of yourself. So there's a sense in which at the microscopic level, there's not a lot that's very distinctive about the Everettian story. It's only kind of delicately true at most that you can start talking about the world in which the particle went left and the world in which the particle went right. You can kind of get away with that, but it's a little bit metaphorical because you can't understand these worlds as things that go off and do their own separate thing because they're going to do that interference experiment we talked about. It's that interference experiment that means you have to talk about both things happening at once. And it's that interference experiment that likewise says we can't think about the things happening at once as being in different worlds, at least as long as worlds are thought about as the kind of things that can't interfere with each other and cancel each other out. It's at the macro level where you ask, how is that everything at once story compatible with the fact that we only observe a single definite macro world? That's the point to which the many world story and other stories diverge.
And I mean, as far as I can tell, all of the theories that you mentioned and the ones that you didn't, they all have their objections. So the Bohmian mechanics, the pilot wave, what are we supposed to make of this ghostly wave that just continues because the wave doesn't collapse, so they're just out there everywhere?
Yeah, that's right. So there's a philosophical concern about those hidden variable theories, which I've argued for at various points. Yeah. How do we get to say that this thing that is structured for all the world like a classical universe does not indeed represent a classical universe? That's the a priori thing we were talking about earlier. I want to say that a priori, the method by which scientific theories represent things is structural. So there's no real space between the state of the system instantiates something that looks just like classical goings on and saying, well, there are classical goings on. Or if there is some space, it's a kind of parochial space. I mean, you might want to ask, look, is a computer simulation of me as real as me? And there's clearly some sense in which I'm different from the computer simulation, but I'm not sure that difference is any deeper than the fact that champagne definitionally has to be produced in certain regions of France. I mean, so something structurally identical to a bottle of champagne but was made in California is not a bottle of champagne. And sure, you can use language that way sometimes. And if you want to say humans, by definition, are systems instantiated in such and such stuff, but not such and such other stuff, you can say that again. But in terms of the sort of deep questions about what's it physically like to be in those situations, what's the epistemology like, could I know I'm not in those situations, the kind of a priori sort of scientific metaphysics I want is structuralist. And the kind of more philosophically serious defenders of sort of hidden variable theories like Bohm's have a thoroughly non-structuralist conception of the relation between the macro world and our sort of scientific representational tools.
Well, just very quickly, I mean, the only reason I mention the ghost waves, or with some of our histories, the path integral and the contention that a particle really takes all possible paths. The only reason I mention those is that each of these theories has aspects that raise philosophical hackles, and it's not just the many worlds theory, even though that's the one that we're going to be focusing on as we turn to some problems that need to be solved.
That's absolutely right. But let me just strengthen it slightly. I mean, so all of these various approaches have philosophical problems, but at least if we're talking about ways you might change the physics and hold on to scientific realism, I think the most serious problem that the realist alternatives to the many worlds theory have are not philosophical, they're scientific. Yeah, my real concern with the pilot wave theory, okay, I'm slightly worried about its mysterious empty wave, but what I'm really worried about is the fact that it doesn't have the resources to calculate the magnetic moment of the electron. Yeah, the theory is just only a very small fragment of our extant science. And so the way I think about Bohm's theory is it's a research project. It's a suggested way we might solve the measurement problem someday. And it's a perfectly intellectually justified, principled task to pursue that research project. I'm not optimistic about its chance of success, but it's serious scientists are doing it. It's worth doing. But it's important not to confuse a research project that might solve the measurement problem someday with a solution to the measurement problem we have in the here and now. And a lot of my disagreement with a lot of the advocates of Bohm's theory is they're too, in their public-facing communications, they're a bit too complacent about how large the gap is between the theory we have and the theory we need to have in order to reproduce the predictive success of quantum mechanics.
Mm-hmm. And am I right then that, I mean, one of the major strengths of the many worlds theory is that it doesn't have this problem that Bohmian mechanics has. It can explain, it has the resources to explain the magnetic moment.
Exactly. It's pure interpretation. It's, I mean, perhaps explain could be contentious. It has the resources to predict the magnetic moment of the electron. And as you said yourself earlier, Everett and Bohm are different theories. Everett is an interpretation of the formalism of quantum mechanics, which is the thing we use to calculate the magnetic moment of the electron. You know, graduate students do this. I did this as a grad student. You do the calculation. It's not that I don't know how to explain that, a la Bohm. I just don't know how to do the calculation, at least to the level of making the empirical prediction as to what a measurement device would actually predict.
Great. Well, turning though to some of the problems, more philosophical, I think, than scientific with many worlds. Maybe the one we should start with is the preferred basis problem, though I think you prefer to just describe it as the ontological problem.
Right. So this is very much the question of what justifies this language of worlds. So if in a certain sense, I've reversed the order here. I've given you an explanation of the many worlds theory that sort of builds in my preferred way of thinking about this, which is to say that things get structurally equivalent to many worlds. But if you just step back and say, maybe at the microphysical level, the way I want to understand the fact that things can be doing two things at the same time is I want to say they do different things in different worlds. Then you've got a problem like how is that justified at all, was the first question. I mean, the theory doesn't, at the fundamental level, say anything about worlds. It just says the particle is doing two things at the same time. And even if you could, this gets slightly more technical, even if you could justify the notion of a world at all, at the fundamental level, quantum mechanics lets you divide up physical reality into definite properties in a whole bunch of different ways. So, for instance, suppose I've got a particle that is it's spinning both clockwise and anti-clockwise at the same time around the z-axis, say. Well, you could try to describe that as saying, well, there's a world in which it's spinning clockwise around the z-axis, and there's a world in which it's spinning anti-clockwise around the z-axis, so there's two worlds. But mathematically, a particle, well, of a certain kind, that's spinning around the x-axis around clockwise and anti-clockwise at the same time around the z-axis, could be redescribed as a particle that's spinning clockwise and anti-clockwise around the x-axis at the same time. And so now you could start saying, well, now there are two worlds. There's one in which it's spinning clockwise around the x-axis and one in which it's spinning anti-clockwise around the x-axis. And those descriptions look incompatible, but nothing in the microscopic formalism will tell you which is right. So the temptation, and people fell into this trap a lot in the 80s, I think, is to say, right, we weren't quite right that the many worlds theory is pure interpretation. We have to add just a little special sauce to it. We have to add a bit of mathematics that will tell us what the worlds are. And the idea was, that was how you solved the third basis problem. You put some math in that said, these are the worlds. But it became recognized that as soon as you did that, you spoiled the main advantage of the many worlds theory, which is this conservatism I'm talking about. I mean, if a multiplicity of Davids is the price you pay for interpreting our best physics and not having to redo quantum mechanics, then maybe that's a price worth paying. If you've got a plan to redo the whole of quantum mechanics, and by the way, it also involves a multitude of Davids, that starts to seem a bit absurd. So it became recognized, I think, that a worthwhile many worlds theory couldn't justify this talk of worlds by a change of the fundamental equations. And then people started saying that, maybe there isn't splitting at all. It's an illusion. It appears to us as if they're splitting. So really, there aren't two Davids. There's just one David, but the one David is suffering something like an illusion that they're having definite experiences, or maybe a different way of putting it is somehow there's one David, but that David has two minds, two sets of conscious perceptions, something like that. And now you're off to some very sketchy philosophy of mind and some things that seem very off the way we want to deal in normal science. And what I think the right way to resolve that is to recognize that it's a false dichotomy to suppose that either worlds need to exist in our theory fundamentally, or worlds need to be illusions, and not really be there at all. It's perfectly possible for things to exist but not be there fundamentally. So Mars and Earth were my examples earlier. Cats don't exist fundamentally. You don't find cats in the equations of the standard model of particle physics. You and I don't exist fundamentally, but we still exist. We're still perfectly serious, robust bits of physical reality. Why is that? Well, it's because we're emergent as sort of autonomous, self-contained dynamical systems, describable in a relatively robust way. That's the criterion in science generally for higher order ontology to be present. If you apply that criterion to the many worlds theory claim, then you get this multiplicity of classical goings on. And that's not something that happens microscopically. That goes back to what we were saying earlier. It's something you see when you're at a sufficiently large scale that the physical processes that govern systems like us start making it impossible for worlds to kind of overlap and interfere, and starts allowing them to just evolve and do their own thing separately from one another.
Can you explicitly bring decoherence in here? It's so important, it's worth just getting on the table.
Yeah. And I should say the physical process that tells us that this interference goes away, that we start getting robust, separate dynamics for these branches, is what physicists call decoherence. And what decoherence is as a physical process is effectively the dispersal of quantum mechanical information from a relatively small number of particles or degrees of freedom in physics jargon, to a very, very large number of degrees of freedom. You see, to do these interference experiments that let us tell that there are two things happening at the same time, it's necessary to bring all the degrees of freedom that are doing two things at the same time into a very delicate coexistence. So if my particle has gone left and right at the same time, I've got to do something that brings the particle, that affects the particle's position in just the right way. If that particle interacted with another particle, let's say it bounced off an electron or something, let's say the original particle was a proton, it bounced off an electron. Now I've got proton left, and proton right, electron right at the same time. And now to do interference effect experiment, I've got to control both the electron and the proton and bring them both together at the same time. If I just do it with the proton, it won't work. You won't see the interference at all. If I just do it with the electron, it won't work. And even with two particles, that's quite a fiddly task. But if you imagine now it's not just a proton, it's a billiard ball, and I've got a billiard ball that's here and there at the same time. Well, zillions of atoms in the atmosphere are bouncing off the billiard ball, every millisecond or something. So now, to do the interference experiment with the billiard ball, and to allow, if you like, the billiard ball world, or the billiard ball left world and the billiard ball right world to interfere with one another, now I don't just need to control the billiard ball, I need to control the zillions of air molecules that bounced off the billiard ball. And that's just impossible. It's impossible for the same sort of reasons we're familiar in sort of thermal physics, that it's impossible in practice for an ice cube to just spontaneously form in warm water, because that would require all of the particles in the warm water to be coordinated in just exactly the right way. So likewise, doing an interference experiment with a billiard ball would require the billiard ball and all the various particles that bounced off it to be coordinated in exactly the right way. That is not in practice possible, either for us as experimenting agents or for the natural processes of the world. And decoherence is that process by which even things much, much, much smaller than the billiard ball interact with many, 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 many degrees of freedom, such that interference can't possibly be seen anymore by any plausible physical process. And it's that process that means that the world language makes sense. The world language makes sense when interference between the worlds won't happen. And the physical mechanism that means interference between the worlds won't happen is decoherence. And decoherence happens basically whenever something gets sufficiently big.
I'm hoping it's okay if I ask, maybe these are more naive questions than I've been asking, but they've always been on my mind and I've never asked them before. But how many worlds are there in this emergent multiverse? Is it finite? Is it Aleph not? Is it the continuum? Can you put a cardinality?
Yeah, okay, good. So it's ill-defined, but at least as big as about 10 to the power of 10 to the power of 20. So the reason it's ill-defined is because there's a bit of convention as to exactly how you carve the world up into worlds, so the universe up into worlds. So my criterion for when I've got two worlds is when they've decohered, when they're evolving effectively independently. But you might imagine deciding to grain them a bit finer and say, well, I won't just consider whether the particle is left or right, I'll consider exactly how far left it is. And now I might say, instead of having two worlds, a billiard ball left and a billiard ball right world, now I've got four worlds, a billiard ball a little way left, a billiard ball a long way left, a billiard ball a little way right, a billiard ball a long way right. And that's still going to work fine because I'm still going to have decoherence, but now I've got four worlds rather than two. And I could keep fine graining like that. And eventually I'll fine grain so much that decoherence stops being present and my assumption that I could treat these worlds as autonomous and separate starts to break down. But there's going to be no very precise moment at which you can say that's exactly the amount of decoherence that needs to be present for there to be worlds, because this is an emergent higher level notion. And exactly how you decide to put that threshold very sensitively affects the number of worlds. So the number of worlds is relative to how we disambiguate worlds, but under any sensible disambiguation of worlds, it's going to be super astronomically large, statistical mechanically large, 10 to the power of 10 to the power of something. It's probably true at least within the observable universe, it's probably any sensible way of disambiguating worlds is going to be finite. So that under any scheme you could come up with here, you'll get a finite number. So the cardinality is probably finite, but ill-determined. And I think one of the interesting philosophical questions Everett throws up is how to think about this kind of indeterminateness. And there are a lot of ways in which you can see relations to some of the extant metaphysical literature on vagueness or indeterminacy. I think speaking of the broader philosophical point for a minute, there's been a lot of philosophical discussion of the Everett interpretation, but until pretty recently, it's mostly been about trying to kill it or prove it or protect it from being killed. It's all about, is it a viable interpretation of quantum mechanics? I actually think there's a very rich range of interesting MLE, metaphysics, language epistemology type questions that one conveys by saying, okay, let's suppose for the sake of argument the many worlds theory is right, and then ask what implications that has for how we think about a bunch of extant questions in other areas of philosophy.
What are some of the parameters that go into one of the equations that somebody might use to try to calculate this number 10 to the 10 to the 20? Because I'm guessing one thing that comes to mind is the age of the universe is probably very important, because that's totally going to constrain the amount of worlds that could have evolved.
Yeah. I mean, if you want to see where I'm getting that kind of number from, I mean, suppose I have some process that leads to world branching. So the kind of process that lead to world branching are things whereby microscopic indeterminacy gets magnified up to macroscopic indeterminacy. So explicit quantum experiments are the obvious one that we've talked about. But classically chaotic things tend to have this character as well. So classical chaos happens when a system is very, very sensitive to its initial condition. The weather is the classic example. If the butterfly flaps its wings, I'll get a hurricane a year from now. If my system is sensitive to initial conditions like that, and if my initial conditions are actually in a quantum superposition of goings on, even if it's a very small quantum superposition, even if my particle is in a superposition of being here and being 10 to the minus 8 meters that away, well, if the system's classically chaotic, that very small difference will get magnified up to a macroscopic difference. So in reality, in the quantum weather system, it's not that the very small differences in the current state of the world will affect whether there's a hurricane next year. It's that it's definitely true there'll be a hurricane next year and not a hurricane next year in different branches. And that's happening as a consequence of the fact that dynamics is so sensitive. So then you want to look in the universe, where are there processes of this kind? And an example would just be the way in which the individual planets around stars form. So, we've got 10 to the power 20, order 10 to the power 20 stars in the observable universe. There's going to be at least one random process associated to each of those, at least one chaotic process associated with the formation of each of those solar systems, the number of planets they're going to have, where those planets are going to be. Those are all chaotic processes. So if I've got some binary process that can happen a different way in each of those 10 to the power 20 planets, then I've got 2 to the power of 10 to the power of 20. Now, you could inflate that number very easily. That was an extremely cautious approximation. Generally speaking, I tend to think once you've established the numbers of the order of something to the power of 10 to the power of something, you've sort of established it's as big as things get, short of infinity. And trying to pin it down further than that is can become a bit of a mug's game. But that's the kind of thing.
Graham's number is a whole lot bigger than 10 to the 10 to the 20.
Sorry, say again?
I said Graham's number is a whole lot bigger than 10 to the 10 to the 20.
Yeah, no, of course. Well, I mean, and 10 to the power of Graham's number is bigger than that, I guess. I mean, that's absolutely right. But from a physicist's point of view, there are small numbers. There are astronomical numbers there's small numbers like 10. There are astronomical numbers like 10 to the 20, and there are stat mech type numbers like 10 to the power 10 to the power 20. And my hunch would be that you'd probably find that quantum branching ends up being a stat mech number rather than some vastly constructible, finite but ridiculously larger number than that. But I don't have a huge amount of confidence in that, second order confidence in that judgment.
Okay. And then the other potentially naive question that I have about these many worlds is how decoherence, or maybe decoherence isn't even the right concept to employ here, but how it relates to special relativity and simultaneity. So does decoherence propagate instantaneously or faster than the speed of light? If something branches, if there's some event, a decohering event, a billion light years away, are we branching here at that exact same time?
Yeah, good. So there's not a naive question at all. It's interestingly contentious in some of the literature. And it's worth saying at the fundamental level, quantum physics is local, which is to say a change in the quantum goings on at a given point can only influence the quantum goings on in the forward light cone at that point. That's just a consequence of the dynamics of quantum mechanics. So what we're talking about is how do you want to think about this at the emergent level of the branches of the worlds? The way I prefer to think about it is that branching is a local phenomenon. So decoherence is spreading out at the speed of whatever interaction is causing decoherence. If decoherence is a physical process whereby the location or whatever other property of an object is being recorded in the states of other objects, then that recording process is a dynamical process. All of our dynamical processes are local processes. They all propagate at sublight speeds. So the branching spreads outwards at the speed of whatever the fastest interaction is that's doing decoherence. As a practical matter, for any large system, that's going to be light speed. So you can think about the branching occurring on the forward light cone of the event that causes the branching. And then there are some subtle issues of non-locality that arise when I ask how that expanding branching process comes to interact with another expanding branching process produced by another quantum splitting event that happened on somewhere space-like separated from me. Now, you can, if you want, or instead of that, you could decide I want to use a global language of branching, and in that sense, you'd want to say that the event of a measurement being made 1 billion light years away causes you to split instantaneously, but that would be conventional. I mean, that would be kind of analogous to the decision to use a certain foliation in describing special relativity. I can describe special relativistic goings-on globally on a given hypersurface and then evolve a hypersurface to a hypersurface, and that can be a useful way of talking. But the choice of hypersurface is a conventional matter, and it doesn't say anything deep about what's happening physically. And so I think that's kind of how I think about the branching of worlds. I think there are lots of situations in which a global notion of world is convenient, but our choice of doing it would be a convention, and the splitting would likewise be a convention. I mean, it's a bit like you probably know this example. I mean, if I travel away, if I travel off into space 10 billion light years, and my wife gets bored waiting for me after 9 billion light years and divorces me, am I divorced immediately? Or do I wait for the signal to catch up? Well, there's a perfectly reasonable set of definitions that says whether I'm divorced or not is a global property, and I'm instantaneously divorced if I've been divorced, in which case divorces are defined on a foliation, but of course it will be conventional whether we defined it. So that change that occurs to me when I am divorced is not really it's a sort of conventional change. It's not nothing physical happened there. There's no violation of superlumin of the speed of light barrier in the fact that my divorce happens instantly.
No, I like that example. That's interesting. Okay, we have gotten the ontological problem on the board. Another, and I think perhaps more troubling for the many worlds theorist problem, it relates to probability. So I guess first, why is probability something that the many worlds theory in particular needs to grapple with? You point to a number of issues. One problem is incoherence, no relation to decoherence. And then the other is the quantitative problem. I think maybe we can just start with incoherence, which if I understand correctly, is simply the question of where probability fits into the deterministic story told by the Everettian theory. And I don't even know if we've explicitly mentioned that the theory is deterministic.
Right, yes. So quantum mechanics is deterministic until you make a measurement. And in the Everett interpretation, measurement is just one more physical process. So it's deterministic all the way through. But the tests we make of quantum mechanics are explicitly probabilistic. I mean, when quantum mechanics is in the business of predicting something like the particle has a 32% chance of being found here when you look at it, and a 68% chance of being found there when you look at it. And on any given run of the experiment, you might get either result. And in the long run, you'll get roughly 32% of here's and roughly 68% of theirs. And on pain of just not being able to reproduce the evidence that supports quantum mechanics, the many worlds theory had better justify that use of probabilistic concepts in the theory. Prima facie, they don't have anywhere to be. I mean, as you say, the equations are deterministic. There's no salient fact of which we're ignorant from a sort of third party God's eye perspective. And the theory says when I make a measurement, there is a me which sees the live cat, say, and a me that sees the dead cat, or rather, there's lots of me's that see the live cat, lots of me's that see the dead cat. But none of that seems to explain why it makes sense for me to say, well, there's a 32% probability of me seeing the live cat. It kind of looks on the face of it as there's a 100% probability I'll see the live cat, and also a 100% probability I'll see the dead cat. So prima facie, there's a problem of asking even whether spaces to inject probability into the many worlds theory. That's the incoherence problem. And then the quantitative problem is, suppose you did understand conceptually how probability could be in the many worlds theory, that's not enough to recover the empirical adequacy of quantum mechanics. It's not, I don't just have to recover the fact that I ought to assign some probability or other to seeing a live cat. I need to assign 32% probability to seeing the live cat. Otherwise, I won't reproduce or recover the viability of the experiments that prove quantum mechanics in the first place.
Right. And if both cases are instantiated, then how are you supposed to assign a specific
Right,
number?
exactly, yeah. I mean, in a sense, there's a slightly artificial dividing the incoherence and quantitative. I mean, insofar as we've got no good reason to assign one probability over another, you can start saying, well, did we have any good reason even to use the concept of probability?
And both of these questions are pretty obviously well motivated. Somebody should want answers to them. But my understanding is that a lot of physicists are not convinced, and philosophers. So, for instance, I spoke with David Albert and Sean Carroll recently on the show, and Sean, of course, is a many worlds enthusiast. But when I asked whether the ontological problem, though I used my own words, is the most significant problem, Sean and David both said, not at all. The most significant problem is making sense of probability. And David, of course, is unconvinced. Sean is not, though he recognizes it's still something that has to be worked on. But how do you like to answer or think that these two objections should be answered?
So I have thoughts about the way we should understand, if you like, a positive solution to the probability problem. But the starting point I'd make is that there's a bit of a double standard going on, because a lot of these conversations assume that probability is something that we find unproblematic in science generally, and which somehow runs into a special problem in the many worlds theory.
Right. But foundations of probability, just to jump in, it's still a very, very lively subject. It is not.
Absolutely. I don't think we have any inherently very satisfactory understanding of what an objective notion of probability would be in the foundations of probability, even apart from the problems that come up in the many worlds theory. I mean, if you look at the kind of strategies we have for objectifying probability, for understanding what probability could be, they broadly fall into three categories. One of them is to deny the idea there are objective probabilities at all, and just say probability is just our personal metric of how much we would like to bet on something or how confident we are of something. That's probably conceptually okay, but it seems to run into a huge problem explaining the fact that we seem to make objective statements about probability in our science. We want to say the half-life of the neutron is whatever it is, 10 minutes or so. We want to say the probability of such and such medical thing is such and such. There's a huge amount of highly objective use of probability concepts in our science that doesn't seem compatible with just getting rid of the concept. Or we could say, all right, well, probability is objective. We better understand what the objective claims are about. And there's a large family of classes that in one way or another are trying to relate probabilities to something like long-run frequencies. The most popular of these days are sort of best system type approaches, but they're all in the same broad spirit of saying the kind of categorical data of how frequently something happens is the foundation of probability. And it remains deeply mysterious how the inevitably quite long-run global facts about frequency that are going on there have anything to do with our probability judgments in the here and now. I mean, you might imagine I've got to choose somehow where either I'm going to be killed if this atom decays in the next 5 minutes, or I'm going to be killed if that atom decays in the next 5 minutes. And I ask God, can you help? And God says, well, I can tell you that of atoms of atoms of this particular species, this is the pattern of their decay, or this is the frequency with which they decay on average across space and time. And for atoms of this kind, this is the frequency. And I say to God, well, thanks a bundle. I didn't want to know about all of the atoms across space and time. I want to know about this atom here and now. And the reasons like that, and a bunch of more technical reasons, have made it really difficult to recover a connection between long-run frequencies and probabilities. And another aspect of that same thing is that it would be nice to imagine that probability can be identified, that in the long run, frequencies converge to probabilities. But we know the best we can do is say that in the long run, frequencies converge to probabilities, probably, and there's a kind of circularity present. And so you end up driven to the third strategy, which is just to say, well, probability is just a primitive. You don't need to understand it in reductive terms. You just understand it. Here's how it works. It's something we have good scientific evidence for. Get on with it. Don't try to analyze it. And I think if you try taking that rather pessimistic description of the philosophy of probability, but I don't think unfair description of the philosophy of probability, and apply it in the Everett interpretation, it's not obvious that Everett does any worse than just general probability does. If you're just allowed to primitively posit probabilities, it's not clear why you can't do that in a many worlds framework. There are things you could say back to that, but at the very least, there's a version of me that say, the experiment has happened, but he doesn't know the result yet, and he can ask, well, how likely am I to see it? He can ask that conceptual term, and if it's just primitive that the right thing to do there is associated with these probabilities, then again, that feels deeply unsatisfactory, but not obviously any more unsatisfactory than it would be in a classical theory. There's a whole bunch of ways in which you can reproduce the general formal claims of frequency accounts of probability in a many worlds context. And I think they're just as satisfactory or unsatisfactory as they are in the single world context. So I think it's a perfectly reasonable move to take. David Papineau is the person who I think is most eloquently argued for this, to say there's no special problem of probability in the Everett interpretation. It just reminds us of a philosophical problem about probability in general. And if for whatever reason we're complacent about that problem, then we haven't any reason to stop being complacent just because we like the many worlds theory. And for what it's worth, my experience of talking to physicists is that a huge number of them have that kind of attitude. In an earlier phase of my research, I was thinking about these probability questions a lot, and I was giving quite a few talks of this to interested physicists. And my experience was it was very hard to get physicists to see that there was a problem with probability in the many worlds theory at all. And after a while, I got quite good at working out how, in the first part of my talk, I could explain to the physicists that there really was a problem of probability, so that in the second half of my talk, I could reassure them that the problem of probability was, after all, not something to worry about. And after a while, it sort of dawned on me there was a rather simpler route to the same result. And so I stopped worrying about persuading physicists how to think about the probability issue. And there are, of course, exceptions, but generally speaking, physicists seem really quite chilled about probability in the many worlds theory. That was the answer to the incoherence thing. Do you want me to... Oh, sorry, that was my sort of tu quoque kind of response. Do you want me to sort of forge on and talk about my positive way of thinking about it?
Yes, the quantitative side. Yeah, I would love to hear that one. That one is more curious to me, how we're supposed to... Yeah, I'll let you go.
But let's be a bit more optimistic. I mean, a different way of thinking would be, if probability is a deep problem, then never mind if it's a problem in classical theories as well. We know classical theories are false. Can we solve that deep problem or make some progress in solving that deep problem in the many worlds theory? And I think many worlds does actually have resources to help us here that aren't available if you don't have the quantum set up. And the reason for that is there's another route to thinking about probability as objective other than frequency. And the other route is to associate probability with symmetry. And you see this in a lot of the way you try to teach probability to kids. You often say, look, here's a six-sided die. How likely is it that the die will land six? And you motivate the idea that the reason it's 1/6 likely is because there's six sides. And you wave your hands in the direction of a principle of indifference or something. And of course, that doesn't really work in itself. There aren't six ways a die could land. There are continuum infinity ways a die could land. If I painted five sides of the die green and one side red, and I asked, how likely is it to land red? And you said 50-50 because it could land green or it could land red, principle of indifference. That's pretty unsatisfactory. If you interrogate those kind of arguments, what you really find going on is some kind of symmetry principle. There's a symmetry between the six faces of the die, such that with appropriate assumptions about the dynamics, you somehow the uniquely appropriate probability distribution to put along the way the die could land is one that respects the symmetry. The problem with those arguments in classical physics is that if the underlying physics is deterministic in single universe, something's got to break the symmetry. because the die actually does land one side or another. If I had a completely symmetric initial state of the die and completely symmetric dynamics for the die, or I should really say if there's a symmetry of the dynamics such that the initial state is perfectly symmetric under that, then it can't land one side rather than another. The symmetry argument would tell you if it was going to land one side, it would also land the other side. There's no indeterminism. So the only way the die can land one way rather than another is if actually the initial conditions break the symmetry, if something specific about exactly how the die was thrown is affecting what's going on. And now you start saying, well, I'll put a probability distribution over those initial conditions, but now we've got to regress, and we still haven't understood what probability is. So symmetry-based ways of understanding probability run into trouble in a classical universe. But in a quantum universe, that argument I've just given, that something must break the symmetry because one thing happens rather than another, isn't available. Because it's not the case that one thing happens rather than another. In a quantum universe, all the things happen. And so my outcome state of the quantum mechanical version of throwing the die can be perfectly symmetric. Each of the individual worlds is not symmetric, but the overall collection of worlds still respects the symmetry. And so you've got the resources to use symmetry-based arguments to motivate or even prove the idea that we should apply probabilities and to particular sorts of probabilities in the in a many worlds quantum setup. And you've got some prospect of actually deriving probabilities from more categorical features of the system, the symmetry features of the system. And there's a tradition of trying to do this that goes back most of 30 years that David Deutsch was instrumental in setting up. And the way those arguments have traditionally gone, certainly the ways I developed them a lot in the 2000s, is to operationalize the notion of probability in terms of my decision-making, so as to solve the problem of incoherence, and then ask what strategies could I adopt in a many worlds framework. So what I mean by operationalize it here is something like, I'm going to toss a coin, make a quantum measurement, let's say, and you're going to give me a big wad of money if one outcome occurs, and I get to choose which outcome I get the money on, but I have to choose before the experiment's carried out. So obviously one strategy I could have is I get the money if the result is the particles here. Another strategy is I get the money if the particles there. And it perfectly well makes sense to use some of the ordinary tools of how we think about probabilistic decision-making to say the kind of strategies I could have here end up being quantified as having the same operational structure as assigning probabilities and betting according to those probabilities. There's a lot more to say there, but basically you're carrying over a lot of the machinery from ordinary decision theory into the quantum setting. And then you can ask, okay, what strategies should an agent carry out? And roughly speaking, if you constrain the agent to adopt strategies that respect the symmetries of the quantum theory, then that uniquely forces the agent to adopt a strategy that's operationally equivalent to the usual quantum mechanical rule. And then if you consider agents whose strategies don't respect the symmetries, you can start showing that those agents' behavior starts getting inconsistent over time in various ways. So an agent ends up in temporal conflict with their other selves. And the reason for that is sort of if there's a symmetry, then you can sort of there'll be quantum mechanical operations that agents shouldn't care about that permute possible outcomes. And you've got the literature for this has got quite complicated. And it's generally described as various decision theoretic proofs of the quantum probability rule. And that description isn't unfair exactly, but I think sometimes it hides what I take to be the really deep philosophical insight that lets us try to solve the probability problem in the many worlds theory, which is that symmetry-based arguments for probability have traction in a situation where everything happens, that they don't have in situations where only one thing happens, and so something has to break the symmetry.
A few things. First, did you study with David Deutsch? Or do you still work with him on these sorts of issues?
I didn't formally study with David. I was directed to him by my undergraduate physics tutor, Arthur Eckert, who's a close friend of David's, when I started asking awkward questions about the quantum measurement problem as an undergraduate. I had a bunch of chats with David as an undergraduate and grad student in Oxford. I had an early draft of his paper on quantum probabilities. So his work had a very substantial influence on me at certain phase in my career, but I would never formally work with David. I mean, David is kind of quite independent-minded as a scholar. He has an affiliation to Oxford, but no formal faculty position there. He doesn't formally take students. So people who end up working with him always end up working with him in a somewhat informal capacity.
Mm-hmm. And then the other thing at more higher level, but I think that some of the language that you use, so agency, decision theoretic, it points to maybe a broader conclusion that can be drawn out of what you said, which is that in this deterministic story, you replace, or one of the struggles or attempts is you're trying to replace objective probability with subjective probabilities. Is that on the mark at all?
No, I want to resist that quite strongly. Although it's a reasonably common, I'd say, misreading of how this literature runs, although this is a contentious question. So the way I would generally think about it is that in modern philosophy of probability, we have a kind of dual notions of probability. We have a kind of subjective, creedal, decision-influencing notion of probability. And then we have some objective quantity that's supposed to be either posited primitively or extracted out of the physical goings-on in the world, an objective chance in David Lewis's terminology. And then we want to establish a certain kind of cohesion between them, such that effectively agents try to conform their personal probabilities, their credences, to these objective probabilities, these chances. And then you have a bunch of philosophical questions about just how that's supposed to go. And I want to say that the thing that plays the role of objective probability in the many worlds theory is the quantum mechanical weight of the branches. That's a perfectly objective quantity defined inside the quantum formalism. It was perfectly well defined in the early universe before there were humans. It'll be perfectly well defined after there were humans. And it's then a substantive claim that the way that quantity plugs into our epistemology is that rational theory testing strategies treat that quantity the way we treat probability in more single world stories. But I don't think that eliminates the notion of objective probability. In fact, if anything, it discovers what the thing in the world is that's the objective probability. Having said which, there's a bit of semantics about this. If somebody wants to say, look, what I mean by objective probability conceptually and analytically requires a single universe, well, you can't argue the definition. If that's the position, then sure, there is no objective probability in the many worlds theory. But there's a different objective thing. Mod squared amplitude is an objective thing. It has the same formal mathematical properties as probability in the decoherent regime. It's in no way subordinate to us in any sense. It's perfectly well definable without bringing agents in. The only point at which you need to bring agents in is if you ask how we could experimentally test claims about it. So that kind of bifurcation of an objective probability-like feature of physical reality and the way we as agents interact with that, I'd say is going to happen in a many worlds account of probability, however you set it up. And I think it's fundamentally pretty similar to the kind of setup you have in a more philosophy of probability single world setup, where you might, for instance, be trying to recover your objective chances as long-run relative frequencies, and then trying to solve the philosophical problem of how those quantities are to be related to our personal decision preferences.
Okay, that's very helpful. For the last few minutes that we have together, I was hoping to address the psychological problems that I alluded to earlier that I personally have with the theory, and I'm not alone because you give them names in the Emergent Multiverse. So the first is the incredulity problem, and in my own words, how on earth are we supposed to accept a theory so wild that it's almost, by wild I mean so, that posits a universe or multiverse so different from the one that we appear to inhabit that it makes it almost impossible to believe? Does this strike you as a merited objection, or it's just one that has to be gotten over?
Well, I mean, in a sense, it's not so much an objection, but just a psychological report. I mean, you're saying to me, how on earth can I accept something that I find so impossible to believe? I mean, frankly, that's your problem.
Yeah.
I mean, we can have a conversation about its scientific merits and demerits. But if you can find some inference from, I find this theory very difficult to believe, to this theory is objectively unlikely to be true, then I'm all ears. But otherwise, that's just a sort of comment on one's capability. I mean, I find it difficult to believe sometimes. I find lots of things difficult to believe. I find it difficult to believe that we elected Donald Trump 5 years ago, 7 years ago. I find it difficult to believe that the cosmos is as big as it is, even without quantum mechanics. These things are all my problem. We've got extremely good evidence that we elected Donald Trump 7 years ago. We've got extremely good evidence of the physical size of the cosmos, and I think we've got extremely good evidence of the many worlds theory.
So, what is it then that makes it hard for you to believe at times?
I think probably just my kind of animal psychology. I mean, I use the Trump comment was just a joke. I use the relation to the physical cosmos advisedly. I mean, do you actually have a sense of how far away the sun is, even? I mean, I could quote you a number. It's 93 million miles away. Do you actually have a visible sense of what that means? How could something ever be that far away? I mean, you could sort of talk about it in terms of how long would you have to drive to get there, but really that doesn't help you understand it. I mean, my sort of vision of the scale of things doesn't really have room in it, intuitively, for something that's 93 million miles away. My brain was not evolved to handle things on that scale. It was evolved to handle distances in the tens of miles and populations in the hundreds, and timescales ranging from milliseconds up to years. Why would we expect that my cognitive capacity smoothly accepts that, and handles and visualizes something 93 million miles away? I have the mathematical tools to kind of get a grasp of that, but there's some sense in which my monkey brain just viscerally struggles at it. I don't think in the visceral resistance to Everett is necessarily so distant from that. I mean, there are perfectly good epistemic arguments one can have about whether the degree of observability of Everett branches is problematic or something, but as far as the straight incredulous stare is concerned, I just think it's a mismatch between human psychology and how weird physics is.
Mm-hmm. I have never thought about trying to wrap my mind around just how far away the sun is. Maybe I should have.
I mean, bear in mind also, that's just a warm-up. I mean, if you think the sun's far enough away, let's talk about the Andromeda Galaxy.
Right. But what I do often find myself trying to wrap my mind around is the speeds at which astronomical objects move at like thousands of miles a second. It's just impossible to wrap my mind around because, like you said, I'm built for terrestrial speeds. That's how my mind works. So the last objection or problem is, you call it the competition problem, which I, again, admit to being somewhat sympathetic to. And in my own words, I mean, why, I don't want to mean this pejoratively, but why settle for many worlds, which seems extravagant in some ways and unparsimonious, at least in the amount of worlds it allows, when we haven't exhausted the possibilities of quantum mechanics that don't entail a multiverse?
Well, I think it's a general question about how science goes. I mean, look, you might suppose you're Immanuel Kant, or a certain slightly caricatured reading of Immanuel Kant, and it's deeply embedded in your theory of mathematics that space is Euclidean, and you learn that physics is now completely committed to general relativity, in which space is not in general Euclidean, and which describes gravity as a curvature in space and in space-time. And you say, well, why should I have to settle for a theory that denies the Euclideanness of space when we haven't exhausted the possibilities of theories of gravity in which space is Euclidean? And I think if you tried that line on most people in physics, they'd be a bit nonplussed. I think they'd kind of say, look, if you've got a concrete theory that's just as predictively effective as our existing theories in which space is Euclidean, let's talk about it and let's do some experiments and things. But if all you're saying is, well, look, maybe I could have some idea which would explain gravity while holding on to Euclidean space, then doesn't seem much more than a kind of pious dream. And I think similarly, I mean, have we exhausted the possibilities of theories in which there isn't a quantum multiverse? I mean, in a certain sense, I'm sure we haven't. The cardinality of the set of theories is presumably countable infinity. We certainly haven't checked them all. But that's not normally how we think about scientific progression. Science is really rather hard. And we have, in quantum mechanics, a spectacularly successful theory. There's no real competition anywhere in science for how successful quantum mechanics is. The theory of evolution perhaps gives it a run for its money. But we've got an amazing theory of this kind. And if we have a way of making sense of that theory that doesn't involve many worlds, fine, let's talk about that way of making sense of it. And if we've got another theory comparably amazing, that's different from quantum mechanics, but just as particularly powerful, well, I'd love to hear about it, and probably so would the Nobel Prize Committee. But absent that theory, I just think it's daydreaming, really, frankly, to just say, well, we don't need to worry about the fact that our current theory seems to have a compulsory many worlds reading, because maybe we'll come up with another one some other day. I mean, to be a bit provocative, you could say the same about the theory of evolution. If you had deep religious convictions against the theory of evolution, you could always say, well, we haven't explored the range of all theories in which organized complexity comes about some other way. And then, technically that's true, but it's not really very compelling.
Well, David, this has been so fun. I learned a lot, and I'm sure our listeners have, about the Everett interpretation. We really covered a lot of ground. So thank you so much for your time and talking about this.
You're welcome. This was a lot of fun.
Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Earhart.